Welcome to E658 VLSI Data Conversion Circuits. This is the first lecture, and as you all know, we live in an analog world. All real signals, okay, that we can sense are all analog in nature, okay, whether it's sound or smell or voice, okay. And unfortunately, fortunately, the world of electronics is largely digital. We see that, cheap programmability and low cost is obtained when a lot of the processing is done digitally. And a digital state machine understands only information at instances of time. Okay, so time is quantized. Also, the register lengths in a digital state machine are fixed. Okay, so if you have, for example, 15-bit registers, it basically means that you can represent how many levels? You can represent 2 to the 15 different levels. So a signal is quantized both in time and in amplitude. Okay. In other words, which is why I keep saying I write in a DSP, time is discrete and so is amplitude. On the other hand, real signals which come from various sensors. For example, this is a microphone. Okay. This, for example, is an antenna. The stuff that's there on your cell phone, and real signals are continuous both in amplitude as well as in time. Okay, so we need to be able to obviously interface these real signals, which are both continuous in time and amplitude, with you need some kind of intermediary who will take these signals and convert them into a form which is suitable for processing by DSP. Okay, and as I just said, DSPs operate with signals internally which are discrete in both in time and amplitude. So that intermediary is basically this interface electronics here, which needs to somehow take this continuous time, continuous amplitude signal and convert it into something which is discrete in time and amplitude, okay, with a minimal loss of information. I mean, clearly you know that when going from continuous amplitude, continuous time to discrete amplitude, discrete time, you obviously will incur loss of information, because while the input is a continuum, if the output has got only discrete levels, there must be some rounding off going on somewhere. That is the role of the interface electronics. And similarly, once the digital processing is all done, finally you need the machine to be able to influence your senses, and whatever we can feel, whether it's sound or an image or smell or touch, whatever, finally has to be converted into analog form. And it's all done by actuators. An actuator is something which converts electrical information into something which is not electrical. In this case, a loudspeaker is, you can consider as an actuator which converts electrical signals into acoustic signals, which we can hear. Just like at the input, you also need some kind of interface electronics between the DSP and the actuator, which converts this bunch of zeros and ones into analog signals, which we can all understand. The focus of this course is obviously not going to be this. Okay. The focus of this course are these two blocks here shown in blue. Okay. And refers to the signal conditioning and interface electronics. Alright. Most of the weightage for the course you can expect to be for the assignments, which I will try to hand out in roughly every 2 weeks or so. And I think all of you have now access to a simulator, so you will. So all the assignments are CAD assignments, which you do on a computer and email me or the TS the assignments. The exams will count only for maybe perhaps I'm planning something like an 80-20 split. So we'll have just one final exam at the end of the course. There's hardly anything you can learn in the course through an exam. And since this is a fairly small class, I think assignments is the way to do it. And I will soon get a course homepage up and running. The contents of the course, as I said, this block here, that's the interfacing electronics on the input side, which converts continuous time, continuous amplitude signals to something which is discrete in time and amplitude. If I have to convert continuous time to discrete time, what is this sample? What is this operation mathematically? What can you call this? This is sampling. Okay. Okay. And continuous amplitude to discrete amplitude. What is this called? Quantization. Okay. So when you say you have to sample a signal, is there something that we need to be aware of when we say we need to sample a signal? Can I just go and blindly sample at any old rate I like? Okay, so according to the Nyquist theorem, if the signal content has a bandwidth B hertz, then it can be sampled at 2B hertz without any loss of information. This is all stuff you know from earlier classes. Okay. So what you need to do, therefore, is to be able to take the input signal, figure out how wide band it is, and you should sample that signal at a rate which is at least twice the band. This is very loosely speaking what is typically done during a sampling operation. We'll get into the math of it a little later, but now, is there something I need to be worried about given Nyquist theorem, and I say my signal is, say, this is the spectrum of my signal, goes from minus B to B hertz, and then I say I will take the signal and then sample it at 2B hertz. Can I just simply sample this, or is there something I need to do before I sample? Please note my question. We all agree that as per Nyquist, if the signal content is B hertz, then I need to sample, the minimum sampling rate I need is 2B hertz. Okay. Now the question is, I have a signal like this. Its signal content, this is the spectrum of the signal. So, and clearly you can see that the signal bandwidth extends from is B hertz. The question now is, can I just simply take the signal and sample it at 2B hertz, and will I be happy, or is there something that I need to do? Pardon? Okay, what is anti-aliasing? That means what? What should I do? So this is the signal. X of t, let's say, and it's got a it's got a Fourier transform like this. In other words, this is spectral, the diagram on top represents the spectral content of the signal. Okay, so then one of you guys says, I must put an anti-alias filter. Let's try and figure out. So what should be the bandwidth of this filter? First of all, why do you need it? Pardon? Okay, so it turns out that typically whenever you have an input signal, okay, there is also going to be noise, and the noise will not be confined to the signal band. There is almost always a lot of noise whose frequency components lie well outside the signal band of interest. For example, the green stuff here shows the spectral content of the noise. Now, if I simply took this the signal x of t, so this green stuff represents n of t, which is noise. So, if I simply took x of t and accompanying it, riding on it is some n of t which has got frequency content well beyond the plus or minus b bandwidth. If I didn't do anything, what do you think will happen if I simply sampled at a rate 2b hertz? What do you think will happen? Again, I will get back to the mathematical rigor of this a little later, but I just want to give you a rough idea of what happens so that you understand why we do what we do. This is the spectrum. For argument's sake, I will restrict the bandwidth of the noise . So this is 4b, this is minus 4b, and when I take a signal and sample it at a rate say 2b, what happens? What do you think happens to the spectrum? If I have a signal and if I sample it at some rate, how will I figure out what the spectrum of the sample signal is? I have to shift the spectrum by the sampling rate and then go on adding them, right? So if I did that, so this is the original signal. And what is my sampling rate? I said it is 2b. So this is x of f plus n of f. This is x of f minus fs plus n of f minus fs. Then I wish I should also have x of f minus 2fs, n of f minus 2fs, and do this for, this is an infinite summation, as you know. But now see what happens. In the signal band, so if I add all these things together, what I will get will be so when I sample the signal, there is no problem because I don't see any aliasing happening. So this is B, this is 2B, this is 3B, this is 5B and so on. Everything seems okay. However, when there is noise, what did we say? The bandwidth of the noise was 4B. So, this was the noise spectrum corresponding to this chap. When I shift and add, what happens? Something like this. Then there will be something like that, and corresponding to the left shift there will be, shift this by a factor of 4 again, another 4. Okay. So is this diagram clear to you? This guy here corresponds to the noise, the spectrum of n of t associated with this chap here. When I shift the signal spectrum, I must pick this, I should split the noise spectrum also. So that is the shifted guy here. Similarly, there is another shifted contribution of the noise here. Okay. And the same thing holds for the rest of the noise spectrum. You understand? So what do you see? There is no problem with signal aliasing. However, what do you see with noise? The total noise inside the signal band is not just what was corresponding to the original signal. In the original signal, in the signal band we had only so much noise. Rest of it was out of band noise. Here what do we see? We see that the signal is there, but the amount of noise in the signal band is dramatically increased because noise from outside the signal band has folded into the signal band thanks to aliasing. Is that clear? So, we'll do it, as I said, we'll spend some time doing the math properly, but I hope we get a physical feel for what's happening. So, even though the signal band is only B, I'd be terribly mistaken if I think that I can simply sample it at a rate 2B. In MATLAB and Fourier and in communication theory, that's all that happens. In practice, there is wideband noise out of the signal band, which would all alias into the band if I wasn't careful. So what do I need to do? Before I sample, I need to simply sampling at 2B leads to out of band noise aliasing into the signal band. So what is the solution? One thing is to say, hey, if we somehow got rid of, we know that anything in the signal band, there is no problem with aliasing. It's only these guys sitting outside which are causing the problem. So, to eliminate the problem, what you do is, one thing you can do is to put an anti-alias filter which has a frequency response like this, so that once you pass the signal through an anti-alias filter, what you have is simply this. This is B, this is minus B, this is signal, this is the noise in band. Please note there is hardly anything you can do about this because they occupy the same frequency band. You can't distinguish this what corresponds to the signal from what corresponds to the noise. So this is the spectrum after the anti-alias filter. And now if I sample this at a rate 2B, what happens? This is what you end up now with. So this corresponds to the contribution from this chap. This noise corresponds to the contribution from this chap, and so on. So you can see that within the signal band there is no problem. Okay. By the use of an anti-alias filter, what we have done is we have avoided the phenomenon of out of band noise folding over into the signal band or aliasing into the signal band. Does this make sense? So when we say we have signal conditioning circuitry, what we mean is that we have this external signal, we need to put an anti-alias filter, then you sample. Okay. So what comes out here is basically a discrete time. Okay. And once you have a discrete time signal, the next job is to quantize. So this output here will have this discrete time and discrete amplitude, and hopefully in this whole process you have not screwed up the signal so badly that it's useless. So the challenge is to basically design circuits which make sure that the signal here is some reasonably meaningful representation of the signal here. Okay, it hardly helps if you've completely destroyed the signal quality in the whole process of sampling and quantizing. And this of course is the realm of analog filters. Some of you have done a complete course on this. This is obviously not the focus of this class. Filters is a specialized area by itself, and there is a lot of theory to this. What the focus of this class is this character here, which involves both sampling and quantization, and this is what is called the analog to digital converter. You understand? Or ADC for short. And this whole process is called data conversion. Okay? So, depending on the system, you would like to have different sampling rates and different levels of quantization. I mean, some systems you may want to quantize very, very finely. For example, in your PC sound cards, you have 48 kilosamples per second. 16-bit A to D converter, alright, which basically means that this is the sampling rate and this is the number of digital lines coming out. So, in principle, the number of levels that you can resolve is 2 to the 16. This is often called the number of bits of resolution, or simply the resolution of the A to D converter. Okay. A layman's view of resolution, 16-bit resolution is equivalent to 2 to the 16 levels. We are able to resolve 1 in 2 to the 16. What is 2 to the 16? It's about 65,000. So this is equivalent to accurately measuring 1 meter in 65 kilometers. The other example is something when you are in your handheld devices, okay. When you have a wireless link, for example, this is the antenna, then you do some kind of amplification. Okay, so this is an amplifier, and since you all taken communication and you know are very familiar with these terms, there is, in the simplest of cases, there is a process which takes these narrowband signals which are sitting at 1.9 gigahertz or 850 megahertz or 900 megahertz or whatever, and moves them down to baseband for processing, okay, and this is called mixing or demodulation. I mean, and then you have to get rid of the high frequency components when you have a mixer. So some kind of low pass filter, and then you have an A to D converter. Okay. The idea in moving the A to D converter up in the signal chain, that is, people always want to put, the holy grail is basically people say, okay, if I am able to put an A to D converter right at the antenna, then everything in the world can be done in software. Correct? So for example, then there is no need, for example, to have to design all these circuits. All that I need to design is one super duper A to D converter and then put it at the antenna, and then if I develop a new generation mobile phone, I don't need to go through this whole process of redesigning these amplifiers and mixers and all this other stuff. It can all be done in software because the entire signal is digitized without using a high resolution A to D converter. Okay. So that is, the holy grail of software defined radio, and if you actually look at it a little carefully, you will find that that's actually quite it's almost an impossible idea, where, I mean, the noise and resolution requirements of an A to D converter, if you had to put it at the antenna, would be some insane number of bits, maybe 20 bits or so with some very, very low noise. So it turns out that such A to D converters are impossible to do. Okay. So then the thing is, okay, we can't push it all the way to the antenna. How far can we push it? So the basic idea is to try and digitize the analog signal as quickly as possible, so that a lot of the operations after digitization can all be controlled in software. Okay. Putting A to D converters is now a routine part of RF design. So as far as the RF designer is concerned, he only has to design the first amplifier which senses the antenna signal as well as the mix. So the number of applications of A to D converters is basically infinite, and depending on the application, the system designer, the fellow who is putting together a whole system, will specify the resolution this PD wants, and it's up to the circuit guys to look at this and say it's doable or it's not doable. So the bottom line is that A to D converters are ubiquitous today and will continue to remain so in the foreseeable future, simply because this is the way systems are being architected today. Okay. So you have analog signals which you need to sense and process, and digital processing is cheap and can today reasonably low speed DSP can be synthesized completely in software without having to know anything about transistors. Okay, it's very easy to design a big complicated digital engine, right? Then once you have a digital engine, you can always write software to do whatever you want. So the key trick is to basically be able to interface the sensors to digital electronics. Okay. On the other side, you have D2A converters. So this is a digital to analog converter. All right. And the job is to take a discrete amplitude, discrete time signal and convert it into analog form. And this is needed, as you guys know, to interface the actuators like a loudspeaker or a video monitor or whatever to the digital engine. One example is you've seen is in your computer monitors, you say the number of colors in your monitor is, you can set it to 32 million colors or 16 million colors or whatever, right? And so how do you get these 32 million colors? At every pixel there is basically something which is red, something which is B and blue and something which is green, and depending on how much you excite these phosphor dots with, you will see the intensity of the red, blue and green can be made to vary in each pixel. Okay. So when these people say you have 32 million colors, it basically means that you can vary each of the red, blue and green in cube root of 32 million ways. So cube root of 32 million is what? It is of the order of 30. It is about 3 or so. Each of the primary color intensity can be quantized to 300 levels. It's basically an 8-bit converter. In fact, the real thing is 256 colors. So it's an 8-bit D2A converter which goes and controls the strength of the electron gun current that you go and hit the phosphor dot with. With that, I'll wind up the class. Tomorrow I'll see you at 11 o'clock.